right, so the last section we're going to look at in Chapter 8, which is really the last chapter that focused on trig, is Section 8.5. And this is on what we call vectors. So lots of applications to vectors when you do physics or calculus. We don't really get into a ton of applications. We do a little, but not a lot. This material is going to be from a different book. So when you see the homework for tonight and tomorrow, it is going to say 5.6 on the PDF, but that is the correct homework. Or I think it'll say 5.5. But anyway, the PDFs are correct in the folders. How many people have studied vectors maybe in like physics or somewhere else? Okay. So anybody that's studied vectors before, a vector is usually used to represent two things. Does anybody know or remember what you use a vector to represent? Yeah?
Like a force?
So a force is an example of a vector, but a force has two parts to it. Yep.
Direction.
Exactly. It has a direction, like which way you're pushing on something, and then it has a how strong component. Okay. So two examples of vectors are force and velocity, because both of these things have a magnitude, which in the case of velocity, magnitude is like speed, how fast you're going. And then direction is what direction you're traveling in. So if you were traveling like northeast at 70 miles an hour, you could represent that with a vector. And then using that vector, we can do different things. We can add it to other vectors, or we can do some other things with it. So an example, let's look at an example of a velocity vector, kind of like a real-time thing. Okay, so here's an example of different planes, okay, in the area, and you could think of each one of these planes as a vector. Each one of them has a speed that they're moving at and a direction. Now, for an airplane, the direction can change, but let's just click on one and see if we can see something about it. Okay, so so I clicked on that one. It looks like this plane landed already. But let's see. I kind of wanted one that was still moving. Or maybe this is the last information. So 529 miles an hour. That would be the magnitude. That's how fast that it was going at some point, whenever that was in the flight. And then if you click on the route is the direction. The difference here is that the direction is changing. So they flew, a certain amount of miles. Like let's say they flew 6 miles on a heading of 278 degrees. Then they flew 37 miles on a heading of 271 degrees. And then a large part of this trip, I think did it say it was from Orlando? I thought it said Orlando to Bradley. I don't know. But anyway, I think it was flying north. A compass heading of north is like 0 degrees, and east is 90. So you can see a lot of the miles on this trip were on headings of like 32, 30, 30, 30, 30, 18. That's pretty much like north and east. So those are the directions that the plane was going. And if we click back, let's just make sure, was it north and east pretty much? Yeah. So it did go west a little bit at first, and then north, but then mostly north and east. And then if you look at the bigger map, so it's the job of each airport to kind of control the traffic in its area, and that's what the tower does for the airport. So they keep track of all the incoming and outgoing traffic, and computers can kind of organize all that information as vectors and know how fast all the planes are going and where they are. It's a little more complicated than what we're going to do because there's so many, and it's 3D. So just because two planes look close, they could be, one could be on the ground and one of them could be at 30,000 feet. So that adds another component to keep track of. But that's one example of how we use vectors kind of in real life to manage something, in this case, air traffic. Okay, we'll also do some problems that look at force as a vector, but that's more for physics. We'll do one question about it, but we don't go into it in real lot of detail. So one way that we can represent vectors is as an arrow. I think when you have a word problem, drawing it out is the best way to do it. Other than that, if you don't have a word problem to solve, it's easier to work with vectors that are written as numbers. We're going to start out by drawing vectors, because I think for people that don't understand it, it makes it very visual, makes it easy to understand. But eventually, we do want to get away from drawing every single problem out, because drawing takes time. That's going to slow us down if we want to solve problems. It's much easier to just do arithmetic than to draw pictures every single time. So when you draw an arrow that represents a vector, that arrow has to represent both parts of the vector, the magnitude and the direction. Well, direction is pretty simple. That's built right into an arrow. I mean, whatever way your arrow is pointing, well, there's the direction. But how are we going to represent the magnitude? And the way we're going to do that is the length of the arrow. So if you wanted to represent an object traveling east, you could do that. And if you wanted to represent an object traveling to the east, but half as fast, you could do that. So same direction, but those vectors have different magnitudes.
Sorry, can you scroll up? Oh, okay.
So any question on the idea of using an arrow to represent a vector? By the way it points and how long it is. Yeah.
Would you have to have an original arrow? Like you can't just have a single one would you have to have another arrow to compare it to for like magnitude? Like how would you be able to tell what the magnitude is just by like length? Is there a standard length set for a certain magnitude?
So normally what you'd have is like if you drew it on a grid, like let's say, let's use like this grid. And let's say you'd have to know what scale that grid is. You know, let's say that each line there represents 10 units. So this is like 10, 20, 30, 40, 50, 60, and so on. If you drew a vector like, actually, you know what, let me use a bigger grid. It'll be easier to see. Let's use this one. My content, pictures. Let's use... let's actually, yeah, let's use that one. And I'll get rid of that one. Let's put it over there. Okay, so let's say each one of those lines represented, 10 units or something like that. If you had a vector, first thing is we'd have to know a direction. You could use like a protractor to measure the angle and draw it. But let's say you had something traveling exactly northeast, and it was traveling, let's say, 50 miles per hour. So then what you'd have to do is, if each one of these is 10 units, you'd have to draw something like this. 1, 2, 3, 4, 5. So that represents 50 miles an hour, because it's 5 units long. And I said northeast. Well, northeast is exactly halfway between north and east. So that's how you would draw a vector that represents something going 50 miles an hour at exactly 45 degrees, or northeast. That's the idea. And you can work backwards from that too. Instead of knowing a speed and a direction beforehand, I can give you a picture of a vector and say, how fast would the object be going represented by that? So then what we can end up doing is making like a triangle, and we could use Pythagorean theorem and find the length of that. That's the speed. And then once we know these two numbers here, that's where we can use trig and solve for the angle in that triangle. And then we can get the direction. So, yeah, we can do it both ways. But every vector has what we call start or an initial point and a terminal point. The initial point is where the vector starts, and the terminal point is where it stops. So these technically are not rays. If you think of a ray from geometry, a ray never stops. Well, these stop. But you could borrow notation from geometry to describe that. So we can describe that as ray PQ. So they borrow the ray notation from geometry as one way of writing this down. I don't use that notation very much, but it technically is one way you could do it. What we like to have is just a single letter. Okay? Not a notation like two letters with an arrow on top, but just a single letter to represent this vector. The problem is in math, single letters are already used for something else. What do we use letters for? We already use letters for variables. So I can't just say that this is ray or vector x and just call it x. Because that's not a variable. This is a vector. They're different things. A vector is an arrow. A variable represents something you don't know. They're totally different. So what could we do? Well, one thing you can do is if you want to use a single letter, you can put an arrow above it. And that arrow above a letter means that it's a vector. That's one way to do it. Or we make the letter bold. That's how we do it most of the time. So as we go on, I'm not going to stand here and take forever to make something look bold. But the idea is, if you see a letter that's bold, that is a vector. Or a letter with an arrow on top. This arrow on top doesn't necessarily mean vector M is pointing to the right. It's just when you put an arrow pointing to the right on top of a letter, it means it's a vector. Which way is it actually pointing? Oh, you'd have to go look at a diagram. Any questions on these two notations, especially that one? 2 days.
Kids. I mean, you want. No, that means you want.
So what we want to look at first is taking two vectors and adding them together. So think about that from the standpoint of forces. Pretend that that was an object that you're going to put some force on. And you had somebody that was going to apply a force like this to it. And then at the same time, somebody else is going to apply a force like that to it. So this person is going to push on that way, and this person's going to push on it that way. So what would ultimately happen to that object? Right, and it would move exactly like this. That vector in blue would be the result of somebody pushing to the right and pushing up at the same time. This is the result. That's how strong the force would be if you measure the length, and that's the direction the force would go in. So the idea is when you combine a vector with another vector, you get a new vector. That's what happens. Combining vectors with vectors by adding them gives you a new one. The new vector can have a different length than the originals. It can also point in a different direction. It depends how the two originals were oriented when you combine them together. But I think showing you that visually, it kind of helps it make sense. So when you add two vectors together, you get a new vector. That idea of forces, you could kind of think of it with like an airplane. You know, if the airplane has a certain speed and direction, but then the wind is also a force blowing at a certain speed and direction, that's going to affect the plane. So the plane may change direction a little bit because of the wind, and it may speed up or slow down because of the wind. You know, the plane has its own power, but then the wind can change it. So it depends whether you're flying into the wind or with the wind, whether it speeds up or slows down. But we'll talk about an example with airplanes where we look at ground speed versus air speed. So like the ground speed of the plane would be if you were on the ground and you could point like a radar gun at the plane and measure how fast it's moving. The air speed would be like if somebody put their hand out the window during the plane, how fast is the wind hitting their hand? Those are two different things. And if you think about it, just like in a car, if you're on the highway and there's no wind at all, and you drive 60 miles an hour and put your hand out the window, it's going to feel like 60 miles an hour. But if the wind was blowing at your car at like 60 miles an hour, and you were driving 60 miles an hour into it, your speedometer is still going to say 60. But if you put your hand out the window, it's going to feel like 120 because the wind's blowing you and you're driving into it. So, but if somebody like on the, like a cop on the side of the road with a radar gun, it's not going to say you're going 120. It's still going to say you're going 60. It's just, there's a difference between wind speed and air speed, and that's because the forces interact. And we'll take a look at that. So, how do we add two vectors graphically? Well, I basically showed you, but I'll do it again, and then I'll write it all out. If you had a vector like this, and then you had a vector like that, and you want to know what's going to be the new vector when you combine those two vectors together. You line them up so that the beginning of one lines up with the end of the other. Just like that. And then you draw a line from where the vector starts to where it stops. So that vector in green would be the result of combining together the red and the black. And if you wanted to do something with that, it's usually easier to do it on graph paper. So now you can make a triangle and use Pythagorean theorem or whatever you want to do. Well, let me write down really everything I just did. So if you want to add two vectors, like v and w, you want to position them so that the ending point of the first vector, ending point of the black one, lines up with the starting point of the next one. That's the part of v right there, the red one. So the first thing is you line them up, and then you draw in a line from where you started to where you finished. And you can follow the path of the arrows to see where you finish. And you could do as many as you want. So if you wanted to know what's going to happen if I take 1, 2, 3, 4, 5, if I take all 5 of those vectors and combine them together, you just stack them all together, beginning to end of each one. And the final answer when you combine them all is where you started to where you stopped. That's going to be what we call the resultant vector of combining them all together.
Wait, so even, okay. So if you started at ground level and you went up like 500 feet vertically, but you only traveled like a foot horizontally and you ended back on the ground, the end vector would just be a foot long.
Well, remember, these are all forces. So this would be like, imagine you had like a box.
Oh yeah.
And you put 5 different like jets on it. And you have one jet on the box pointed up at a 45-degree angle with that much power.
So,
Then you put another jet that's going to propel it to the right. And another jet that's going to push it down and to the right. the end result of all those jets is going to pretty much make the box go in a straight line to the right.
Yeah, never mind. Because if it was distance.
Yeah, no, it's more of like a distance and direction. Yeah.
Never mind.
And this would be kind of a waste to set up something like that because you've got forces fighting each other, right? You've got you got a jet here that's going to be pushing it down a little bit, another one that's pushing it down, and then you've got jets that are pushing it up. And the up and the down is basically canceled out in this picture because it's almost horizontal. Not quite, but almost. So you got a lot of wasted power there. So to figure out the result, draw a vector from the start point of the first one to the end point of the last one. Usually we only add 2 together, but you can apply this for as many vectors as you want. So one downside to drawing this is you might need a pretty big piece of paper, depending on how many vectors you have, depending on how you scale it. If your graph paper goes by ones, that's not a very big scale. You could go off it real easy. But that's the approach we're going to use when we do a word problem. We're gonna draw it out. We're going to look at the forces in the picture and try to visualize what's happening. That's the easiest way to do it. And look at the notation I'm using here. I decided to use the letter with the arrow on top to represent vectors. But I think later on or tomorrow, I know I'm going to use bold letters. The other thing about bold letters, it's not a huge issue now, but before you had computers, and maybe even some people like on computers, how are you going to take a letter and put an arrow on top of it? I don't know. If you're texting about vectors, how are you going to do that? How are you going to put an arrow on top of a letter? That's a big deal, right? You guys talk about vectors, right? Yeah, of course. So maybe you can do bold. I don't even know if you can bold something.
You can bold up text.
No, so I don't even know. You might be in trouble. We'll have to invent something so you can talk about vectors.
Where can I talk about vectors? There's nowhere we'll let.
Okay, so I want to add v and w together. You don't really need an x-y axis. All you need is a grid, because if you want to measure it when you're done, that's how you can measure it. Okay, so if I want to add these up, how would I do it? Yeah.
You would place V on the graph.
Yeah.
And then connect the initial point of W to the terminal point of V.
All right, so yeah, plenty of space right about like that. And what do I do to finish it up?
To the terminal point.
Connect the initial point to the terminal point, and that is what V plus W, and these should be bold, but we talked about that. That's what V plus W looks like. So these vectors definitely aren't fighting each other. One of them's pointing down and to the right, one of them's pointing to the right. So they're kind of working together to make the object go even further down and to the right. Okay. Any question on that? So that's the first one. Let's look at this one. We've got V and W. And what do you think is going to happen when we add these together?
It's going to become nothing.
Right, you're going to cancel out because you need to line up that dot with that dot. That's how you add them together. Connect the end of V to the beginning of W. And then once you line up the red dots, you're going to look and connect green dot number 1 to green dot number 2. So you don't worry about the green dots right away. All right? We just look at lining up the red dots and then connect green 1 to green 2. But when you line up the red dots, it also lines up the green dots. which means there's nothing to connect. I don't have a diagonal there. So in this case, there's no real picture we can show. But the answer is still a vector. Because when you add two vectors, you always get a vector. That's the rule. So what do you think we're going to call this?
Like vector 0.
But yeah, the zero vector. So what we would do is write this. You can either write the zero vector, or you could write this. Either one of those. The zero vector is the only vector that does not have a direction. You know, we said all vectors have magnitude and direction. Well, this one has magnitude. You could say it's 0. So magnitude 0. And the direction doesn't have one. So it's called the zero vector. So it turns out when we add vectors, we can use the commutative property, and we can also use the associative property. So remember, commutative means if you change the order, you still get the same result. Well, let's try it. I have two vectors, v and w. And I'll add them first with v and w, and then I'll change the order and do w plus v. Okay, so here's v. Here's w. And again, these vectors are kind of, like the arrowhead is kind of thick, so it's hard for me to know exactly where I should put it, but I'm just going to try to put it like in the middle of it, or on the tip of it, kind of. Yeah, it's the best I can do. That is the one on the left. That's v plus w. Now, let me switch the order. Let's do w and put v on the end of it. So I just put w first, I put v second, and now if I connect it, again, it's just by hand, so it might not be perfect, but it's pretty close. So it comes out the same. Any question on the commutative property? So it doesn't matter how you do it. Now, associative is not an order, it's a grouping. ABC, ABC, same order. But the question is, like, its order of operations, like what group are you going to do first? And it doesn't matter. It's just like adding the numbers. So let's do it on the left, and then we'll do it on the right and see if we get the same thing. So here's A plus B. Yeah, if I used a ruler or my tool, it would probably come out better. That's A plus B. Now, take and put C on the end of that. It doesn't quite cancel it out, but it brings it back a little bit. So now connect where you started. Right about there maybe. That's where you finished. So that's A plus B plus C. Now, let's do it the way it says on the right. Take B plus C first. So here's B plus C. So there's, that's not very straight. Alright, so that was, I think it was like that. So that's B plus C. And now take and put that on the end of A and see what happens. Let's put that right about there. Draw that. And if we match it up, again, this one might not come out quite as good, but it's still pretty good.
Oh, yeah.
Matches up pretty well.
But you can see you get the same thing. So the point here is vector addition is commutative and associative. Not really a proof, but it kind of illustrates the idea. All right, so what do you think the difference would be between vector v and the negative of vector v?
Opposite direction.
Opposite direction. Okay, what would be the same? Yeah,
Magnitude is the same.
magnitude would be the same. So the difference is the direction they point. And can anybody be more specific about the direction they point compared to each other?
Is it reversed? Or the opposite?
Yeah, it's exactly 180 degrees opposite direction. So when you put a negative in front of a vector, it doesn't change the magnitude, but it changes the direction. And a negative in math has to do with what operation? Subtraction. So that should give you an idea of how you can subtract two vectors. All it means to subtract a vector is to flip one of them around and then add it. But we'll look at that right now. I think we already saw that earlier. If you take two vectors that point in opposite directions and you add them together, technically that's wrong. That's not how it should be written. It should be written like that. So adding two vectors that are opposites of each other gives you the zero vector.
So in the other example, where we got the zero right before, was W just the inverse of V? Where we got,
This one?
yeah.
Yeah, so you could really say here that W was the opposite of V. So really you were adding V and negative V together. Yeah. So now let's think about something with numbers, and then we'll apply the same idea to vectors. What if I wanted you to do that, and you didn't know how to do subtraction, but you know how to do addition? How could you rewrite this as an addition problem?
Plus negative.
3 plus negative 2. Well, we can do exactly the same thing with vectors. If you want to subtract two vectors, you're going to make it an addition problem. But what you're going to do is add the opposite of the second vector. And opposite really means what again with a vector?
180 degrees.
Yeah, it means flip the direction. So to subtract two vectors, find the opposite of the second one, and then do addition, just like I told you. We'll try an example of that. So find the opposite of the second vector, and then add. Okay, so they want us to do V minus W.
I did say on the opposite of the second.
Yep, and add. So I'm not going to think of it as subtraction. I want to think of that as addition. So how can I rewrite V minus W?
V plus negative.
Right, I want to add this vector to that vector. Well, I've got V. Now I need negative W. Well, to get negative W, just flip it around 180 degrees. One way I can do that up here is to reflect it horizontally and then reflect it again vertically. And if you do a horizontal followed by a vertical reflection, that rotates something 180. I don't have a button that says rotate 180 up here. That's how I. Okay, so now we've got V. We've got negative W. Add them together, and that will answer the original problem. So here's V plus negative W. And there you go. That's V minus W. Any question on subtracting two vectors? All right. So we've added two vectors. We subtracted two vectors. We are not going to multiply two vectors today. Okay, multiplying two vectors, that gets a little different. Because one thing that's a little unique about multiplying vectors is there's two ways to do it. You might think, well, what do you mean two ways? Well, when you multiply with numbers, there's only one way to do it. If you want to do 3 times 2, you get 6. There's no other answer. But if you wanted to multiply vector v and w together, one way to multiply them is called a dot product. Another way is called a cross product. And they're different answers.
Dot and cross what?
Dot and cross product.
Cross product.
Yep. So when somebody asks you to multiply two vectors, they have to specify if it's a dot product procedure they want you to do or a cross product. Well, cross product only applies to 3D. So if you're doing something in 2D, then you know right away which one it is because cross product doesn't exist in 3D. But what we are going to do, a kind of multiplication, but not a vector times a vector. It's called scalar multiplication. Now, when you think of like scaling something, well, what does that make you think of? Like if you scale something.
You grow or shrink something by
You can grow, what'd you say?
you grow or shrink something by factor.
Yeah, so there's a factor that you multiply something by, and it either grows or shrinks. So sometimes if you're building like a scale model of a house, generally I would say you're building a smaller version of the real house. If you build a scale model of like an atom, you're probably building a bigger model of what an atom really looks like. But it's basically a bigger or smaller version controlled by what we call a scale factor or a scalar. When you stretch or lengthen or shorten a vector, the result is a new vector. And the way that a scalar product would look is if this is a vector and I wanted you to scale it, that's what you would write. Just to be clear, that is not a vector times a vector. That's a scalar times a vector. It's a number times a vector. Now, there's actually 3 things that can happen when you scale a vector. What's one thing that can happen to it? Yep, you get longer. What's another thing? Smaller. Staying the same. I don't want to count that. That's not even scaling that. But there's one more thing that can happen. It can change direction if you scaled it by what kind of number? Yes. If you scale it by a negative, it can lengthen, shorten, or it can flip the direction 180 degrees. Those are the 3 things that can happen when you scale. So this is an example of a scaling that would make the vector half as long. This is an example of a vector that would be 3 times as long as the original and point the opposite way. So now we're going to talk about visually how do you scale a vector like on graph paper. I'll show you that right now. So find 2v. Well, here's v. How do you think you would get 2v?
Would you add?
Okay, just add v to v. So that I can do exact on the board. There's v. There's v. There's 2v. Okay. Now, 1/2 v, I mean, yes, I could do it on graph paper. If I knew this was like 10 units, I would just make it 5. I can't really do a 1/2 v on the board exact without some kind of measuring. So I'm just going to estimate. 1/2 v might be like that. That's a half. Any question on those two?
So with scaling, you'll always have an original one that you base it off of?
Yeah, and eventually we're going to have an original one that's not an image, but rather a set of numbers. Like we're going to be writing vectors like this.
No.
And then we can, like if you wanted to scale this vector by 5, well, you don't need to draw something 5 times as big. You just have to write 10, 15. And that's how you do it as numbers. It's kind of like a distributive property.
Yeah, that's like an ordered pair, right? It's like the endpoint of the vector.
No, it's a vector. And it doesn't represent a point. It represents a horizontal and a vertical component,
Oh, I see.
which
So
I'm going to
it's-
show you.
Okay.
Actually, I'm going to show you, yeah, right here. So a few more visual things to do, and then we'll do that. All right, let's try this one. How would I get negative v? Yeah, I'm not going to even do it fancy. I'm just going to go like this. Okay, so there's negative v. How about negative 1/3 v? Yeah, just take 1/3 of that. So maybe like that. There you go. So negative flips it around. And then the number can shorten or lengthen. Let's just do one of these. Let's just do the first one. 2v plus 3w. So when I do this, how many individual vectors am I going to be stacking together? 5. I kind of need to look at them and know where they're going to go, because I need to start with v somewhere. I mean, do I want to start it right here? Do I want it over here? Up there? Well, v is up and to the right. W is down and to the left. So I'm going to be doing a lot of movement right. So I need to start on the left. And I'm going to be going up a little bit. I'm going to be going down a little bit. So I'd probably just kind of stay in the middle. That's probably pretty good. All right, how many V's am I going to stack together? 2. So 2 of them. And how many W's? So we need 3 of those. So there's 1. There's 2 roughly, and 3. Good enough. And my final answer is going to be, how do I get that?
Starting
The very initial to the very end.
Yep. From here to there. That's 2v plus 3w. And those were small enough, and we had a big enough piece of graph paper, not really an issue. But we want to get a better way to add these up eventually, okay, than having to draw it. Okay, this symbol. Okay, when you put double bars around a vector, those double bars mean magnitude. In other words, they're asking you to find the length of the vector. Now, length is what kind of value?
length is vector.
Length is not a vector.
Scalar. Wait,
Well,
what?
well, it could be a scalar, but a scalar is really just a... What types of things can be scalars? Can you scale something by a vector? It's just a number, right? So magnitudes are numbers. Magnitudes are just numbers. And because they're distances, which that's what I kind of wanted to get at. They're distances. Distances are always what kind of number? They're always positive. So it doesn't matter if your vector points down. It still has a positive magnitude. Pointing down is the direction. The magnitude is how long it is. It doesn't matter which way it points. So what would be the difference between those two? The magnitude of v and the magnitude of negative v. It would be the same thing. There is no difference between those two calculations. They are the same. It's like saying, what's the distance from here to Boston? and then taking the same route, what's Boston to here? That's the same thing. We're just going opposite directions. Now, if the magnitude comes out to 1, that is something special. Does anybody remember when we studied circles that had a radius of 1? What did we call those circles? Unit circles. So what do you think a vector is called if it has a length of 1? Unit vector. So not all vectors are unit vectors, just like not all circles are unit circles. But if the length of the vector does come out to 1, then it is called a unit vector. A lot of vocabulary used first. Alright, so we've done a lot visually. And I think visual is great for a word problem to try to see what's going on. But if we just want to add, subtract vectors, we need a better way than drawing it. Drawing is going to slow us down. Plus, if you've got to scale something like thousands of times bigger, I mean, what are you going to do? You get a big piece of graph paper, you can scale your tick marks, like, it just gets kind of annoying. So one way we can represent vectors is with this notation with 2 angle brackets. And if I show you an example before I write everything down, I think it'll help it make a lot of sense. The vector 2, 3 looks like this. That is the vector 2, 3. The idea is if you look at your vector and you made like a triangle out of it, you look at the horizontal distance you traveled and the vertical distance you traveled. This is 2. That's 3.
Say no worse.
That's the thing. That notation doesn't tell you where to start from. We're going to talk about that. So A and B are what we call the components of the vector. If we were doing it in 3D, we'd put comma C. And then we'd have an x-axis component, a y-axis component, and a z-axis component. When we're dealing with 2D, we can really say the left and the right and the up and down component. When you get into 3D, you can't really say left, right, up, and down. It gets confusing. So we call it the x-axis component, the y-axis component, and the z. Okay, so that's the horizontal, which is the x. That's the vertical, which is your y. So A tells you how far left and right you go from an initial point to a terminal point. So that's like your A. And B tells you how far up or down to go to get to the terminal point. So this would be the vector A, comma, B. A and B are like directions. Horizontal movement followed by vertical movement. And by making A and B any combination of positives and negatives, you can move in any direction you want to go. And A and B could also be fractions. Like if you wanted to go 1.5 units right and 2.5 units up, you can use fractions for the A and B. I kind of already said that. So A is horizontal component, B is the vertical. At least in 2D, you could think of it that way. So this is the question that Ben kind of jumped in and stole my whole thunder here. I was going to talk about it. Unreal. So where does it start from? Well, it doesn't really tell you. This notation just says you can start anywhere you want. So if I want to draw the vector 2, 3, and that's all the direction said to do, then where's my graphic? There it is. That's the vector 2, 3. That's fine. This is also the vector 2, 3. This is the vector 2, 3. This is the vector 2, 3. Those are all the vector 2, 3. This notation doesn't tell you where to position it. And with vectors, a lot of times it's not about the position of where the arrow is. It's about how long the arrow is and what direction it's pointing, not where you put it. But there is a common place we usually put it if we're given a choice. Where do you think the most common place to put it is?
Origin?
Right. The most common place to put it is having the initial point at the origin. And if you draw it with the initial point at the origin, that's called a position vector. So the initial point would have a coordinate of 0, 0. So last thing we're going to look at is how do you take a vector that's not at the origin and find out what it would be if you put it at the origin. And that's what I'm going to show you. Now, we already know this is the vector 2, 3. Let's pretend we didn't have these elements. Let's look at just that one. What's the coordinate of the initial point? Right there.
Sorry, what was it called when it starts with origin?
Position vector.
Position vector.
5, 2.
So 1, 2, 3, 4, 5, 2. And what about that? Well, this is 0, 0. So 5, negative 1, that would be like over there. 7, 5. Which one of those, let's just call this one 1 and 2. Which one is the initial point? 1. And the terminal point? 2. I picked 1 and 2. Now, does anybody see what you could do with these coordinates to get that vector?
Subtract them.
You subtract them. If you take terminal minus initial, has to be in that order. 7 minus 5 gives me 2. And 5 minus 2 gives me 3. That's how you can find a position vector if you're given an initial point and a terminal point. So it's kind of like converting the start and the stop point into a vector, which now I could say, oh, it's just 2 to the right and 3 up. So I can draw it anywhere I want. There. All right, so to find a position vector, first of all, you would have to know the initial point and the terminal point. Whether they're called P1 and P2 or Z and Z1 or whatever you want to call them. But as long as you know the initial point and the terminal point, the horizontal component of your vector is terminal minus initial for the x's. And the vertical component is terminal minus initial for the y's. And you could probably guess if we were going to do it in 3D, there'd be one more component on the end here that represent the z-axis. And we do the same thing. So every formula that we're learning in 2D, you can kind of think of the 3D part as coming out to 0. That's why we're not writing it. Okay, so lots of different vocabulary. Terminal point, initial point, position vector, 0 vector, magnitude, direction, all that stuff. It's all terms we're going to use throughout the week. Okay, so find the position vector. You don't need to draw this. The goal is really to find the horizontal and vertical components. If you subtract them in the wrong order, you'll get a vector that points exactly the wrong way. So don't, it's got to be the right order. What's going to be the calculation to find my horizontal component?
Would it be 4 minus -1?
So 4 minus -1. And what about my vertical? 6 minus 2. So what would be the notation for the vector represented by that initial and terminal point? 5, 4. And again, I don't know if I mentioned it clearly. I think I wrote it. But that's called an algebraic vector. At least that's the notation our book assigns to that name. Now, that's not the only way to write vectors. It's a step better than drawing it, because now at least we don't have to do as much drawing. Like if you wanted to add this vector to it, you're just going to say 6, comma 7. It's easy. You don't have to draw anything. But tomorrow, or whatever the next class is, we'll talk about the final notation we're going to use, which is it's pretty similar to that. But it's the notation that's most common, and we're going to use that the rest of the module. Okay. Questions on that? Okay. So remember, homework, it's a different PDF. It does not say 8.5, but just go to the 8.5 folder and I put the correct PDF. On 26 to 32, they give you directions in the book that you are not going to be able to do yet. So on 26 to 32, I want you to find the position vector. Okay, so 1 through 10 all, 14 to 22 even, and 26 to 32 even.